In this video, we take a look at the different number systems or bases that you need to know about. These include binary, denary, and hexadecimal. So denary, or the base 10 number system, is the number system which you will be most familiar with. It's the one that you've been learning ever since you were a small child, ever since you first started to count. It contains just 10 unique digits, 0 through to 9, hence why it's known as base 10, because there's 10 unique digits available. Now, incidentally, why do you think our number system has evolved in this way? Well, the answer is that no one actually really knows the answer, but it could quite possibly have something to do with the fact that we have a total of 10 fingers and thumbs, so it became natural to count up to 10 on our digits. With the denary system, we have no unique digit for the number 10, or indeed for any number higher than 9. We have to put the digit 1 and 0 together in order to get the number 10. So let's look at how that actually works with larger numbers. Well, we'll start with the 10, and obviously I've written that out here. Now I've got two leading zeros on the beginning, but that doesn't affect the fact that this is the number 10, 0, 0, 1, 0. You will know from basic maths at primary school that the weighting of the headings in each of these columns goes up by 10 each time. So what I have here is 0 to thousands plus 0 to hundreds plus 1 in the tens column plus 0 in the ones column, so the number 10. If we take a bigger number now, so 4273, the exact same principle is applied. The column on the far left is our thousands column, so we have 4 times 1,000. We add that to the next column, which is 2 lots of 100. We add that to 7 lots of 10 and 3 lots of 1s, with 4,273. Now, of course, we don't perform that calculation in our head. When we see the number 4273, we are so used to it now that we simply read it straight out as 4,273. Notice once again how the column weightings, that's the headings, are increasing by a factor of 10 every time we move one space to the left, and this is because decimal is a base 10 number system. Now, along with our base 10 denary number system that we're all well aware of, there are two other base number systems you have to become familiar with for GCSE, and we're going to take a look at those now, and that's base 2 binary and base 16 hexadecimal. So with the base 2 binary number system, we only have 2 unique digits, so a 0 and a 1, and that's it. All other numbers in binary must be made up of a combination of these 2 digits. So what is the number I've got represented here? Well, the first thing you'll notice is the weighting of the column headings has changed. Starting on the right, we have the 1s column, then the 2s, then the 4s, then the 8s. It's doubling each time, or timesing by 2, and that's because we have a base 2 number system. So we just apply the same rules we did for the decimal system. Here I have 0 lots of 8s added to 0 lots of 4s. I've got 1, 2, and I'm adding that to 1, 1. So the number 1, 1 in binary is 3 in decimal. And you need to read this as 1, 1, and obviously not 11, because an 11 is a decimal number. So let's do exactly the same thing, but this time for a slightly larger number. The process, although, is identical. So starting on the left here, I have a 1 in the 8 column, so I've got 1 lots of 8. I'm adding that to 0 lots of 4. I'm adding that to 1 lot of 2, and finally 1 lot of 1. So I have an 8 plus a 2 plus a 1. So this number is 11 in decimal. So the binary number 1011 is 11 in decimal. And again, just to reiterate, the weighting of the column headings is timesing by 2 every time we move to the left, because binary is a base 2 number system. To represent bigger numbers, you obviously need to add more columns. In the exam, you need to be able to read, write and understand numbers of up to 16 bits in size, so that's 16 columns. This obviously gives us a range of numbers that you'll need to be able to represent. Starting on the right with 16 bits, we have a column weighting of 1, and then doubling by 2, our column weighting goes up to 2, 4, 8, 16, all the way through to the most significant column representing the value 32,768. When considering positive numbers, this means if we put a 0 in every column, the smallest number that can be represented in 16 bits is 0, and if we put a 1 in every column, the largest number that can be represented is 65,535. So hexadecimal is a base 16 number system, and it follows exactly the same principles as the other number systems we've just been looking at. The only difference is with hex, we have 16 unique digits. Now, this obviously presents us with a bit of a unique problem. What do we use to represent the hex digits 10 to 15? We can't simply use our decimal numbers 10 for 10 or 15 for 15, as these are two digits stuck together. Well, we simply choose to replace digits 10 to 15 with the alphabetic letters A through F. So in hex, we have 16 unique digits representing 0 to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, and then A representing 10 from decimal through to 15 for F. So let's just summarise and recap those three base number systems and look at them all side by side, counting up from 0. So in the left column we have base 10 denary, followed by base 16 hexadecimal, followed by base 2 binary. So all those number systems can represent the number 0 in a single digit, and they can all represent 1 with a single digit. Of course, as soon as we get to 2, we can represent a 2 in base 10, that's fine, and also in hex. But in binary, we've now run out of unique digits. We only have a 0 and a 1 available. We now have to combine those zeros and ones, as shown earlier, in order to represent the denary value 10. So in binary, the denary value 10 is 10, and remember it's important to read that as 10 and not the number 10. We can proceed in a likewise fashion all the way up until we reach the denary value 9. Now, of course, after that, we don't have a single digit in the denary system anymore for representing the digit 10, so we have to combine digits. And again, in hex, we now have to do something special as described earlier, and we have to switch to using letters, because hex allows us to represent values above 10 in denary in a single digit. So in denary, we have 10 or 10, in hex we have A, and in binary we have 1010. This continues all the way up to the denary value 15, which is the hex equivalent F, and the binary equivalent 1111. Of course, we can carry on going above that, and as soon as we do, hex no longer has a single digit which can represent a value. So we'd now have to start combining values, just like we have been in denary and binary. So let's just quickly recap. Computers use different base number systems. There's binary, which is base 2, which contains just a 0 or a 1. It's easy to represent two states in binary, such as on, off, or a high or low voltage. Denary, which is the number system we're most familiar with, is base 10 and contains unique digits 0 through 9. And finally hexadecimal, base 16, which contains the digits 0 through 9, followed by A through F. Hex numbers can be expressed more compactly than binary numbers, and this has several advantages, which we take a look at in another video.